So in day 4, we're going to be looking at binomial expansion, specifically focusing on Pascal's triangle. Now, we all know how to do this from grade 9 and 10, where if it's the exponent of 2, that's how many times you would write a base. Like so. Then we'd use FOIL to insert one into the other, and then collect like terms, like so. And that would be your final answer, because you can no longer break it down and collect like terms. But what happens if you have a question with a higher exponent like this, 7 for example? And so on. You would have to write that base 7 times, and then FOIL this one into that one, find the answer, this one into that one, find the answer 7 times. Now, what Pascal's triangle does is allow us to solve questions like this with bigger exponents more efficiently by giving us some preset coefficients.
What we mean by predetermined coefficients is that we use the exponent that is in the question to determine what row of the triangle we use. In this case, since we have a plus b to the third exponent, we're going to use row 3. And to create my triangle, I always start with row 0, because anything to the power of 0 is 1. And each row must start with a 1 and end with a 1. So I have ones coming down this side and ones coming down this side. And if I continue the triangle, it'll look like this. So each row, to get my next numbers, I'm simply adding the 2 numbers above it. So in this case, I add the 3 and the 1 together, and they come down and I get the answer of 4. Just like down here, I'll add the 10 and the 10 together to get 20. And that is how you get the next row. A simple checklist to building Pascal's triangle is just to make sure that you start each row with 1, and each of the following rows start with 1, and add. This is the first example we have, and the question is a plus 2 to the 4th exponent, and since the exponent is 4, we know that we're going to have to use row 4 of Pascal's triangle. We will start by first putting in the coefficients. Now that we have all of our coefficients, we can take the first number of the binomial, which in this case is a, and put it into the answer. Since we have an exponent of 4 in the question, we put an exponent of 4 on the first a, and begin to count down until 0. After this is completed, we can take the second number in the binomial, which in this case is 2, and also put it into the answer. And now we can start with 0 on the exponent and count up till 4. Now that this step of the equation is complete, we can begin to solve for the exponents. After this is completed, we group like terms, and since we have no like terms, the question is completed and we're done.
So now we're going to move on to example number 2. We have a binomial to the power of 5. Therefore, we have to use the fifth row of Pascal's triangle, which is 1, 5, 10, 10, 5, and 1. And I've listed them all here, as you would as well. So now we're going to take one of the numbers from our binomial, and we're going to list it after each coefficient. But the first one you choose is going to start with the power of 5, and then count down 4, 3, 2, 1, and then 0. Now, normally we would not write 2a to the power of 0 because we know that anything to the power of 0 is 1. And we would not write the exponent of 1 because we know that if nothing is listed like that, we know it's to the power of 1. So now I'm going to do the same thing for 3, our second of the two numbers, but this time the exponents are going to go from 0 to 5. So now our next step is to just apply the exponents into our bracketed numbers. But we have to remember that this exponent here applies to both a and the 2. So we're going to start with 1, and we know that 2 to the power of 5 is 32. So it becomes 32a to the power of 5, and then we know 3 to the power of 0 is 1. So times another 1. And then here, we know our 5, and then 2 to the power of 4 is 16. And that becomes to the power of 4. And then 3 to the power of 1 is, of course, 3. Here, we know 2 to the power of 3 is 8, and 3 to the power of 2 is 9. Then this one's going to be 10 to the 4a squared, because the 2 to the power of 2 is 4, and a squared is a squared. And then 3 to the power of 3 is 27. Then here we have 5 times 2a times 3 to the power of 4, which is 81. And then 1 times 2a to the power of 0 we know is 1. And 3 to the power of 5 is 243.
Now that we have our exponents into the equation, all we have to do is simply multiply. So now that we have no like terms, we are done the equation, and we can check that we are right by making sure that our exponents start at 5 and continuously go down all the way until 0. Now on to the third example. In this question we have 3x plus 4y, the fourth exponent, and since the exponent is 4, we know that we will use row 4 from Pascal's triangle. And as always, we will begin with the coefficients. After this is done, we can take the first number from the binomial, which in this case is 3x, and plug it into the equation. Now since we have the exponent of 4, we're going to have to start with the exponent of 4 and count down all the way to 0. After this is complete, we can take the second number of the binomial, 4y, and put it in. Since this is the second number in the question, we will begin with the exponent of 0 and count up to 4. We will now solve for the exponents.
So now to finish off the question, we're just going to straight up multiply and then after collect like terms. So 81x to the power of 4 times 1 is 81x to the power of 4. Keep in mind that how I know that I'm right with the exponents is that they all add up to the one in the question. So 3 plus 1 is 4, 2 plus 2 is 4, and so on. Three plus 1 is 4. And now, a way that I check that my exponents are right is that my x's, as written up here, start at 4 and count down to 0. So we have 4, 3, 2, 1, and then 0. And then my y's count up. And then I would collect like terms if there were any. And that's about it. We're done that question. So what I have here is just to further your understanding on why the numbers in the Pascal's triangle are like that. So here we have an example, a plus b to the power of 2. So I did it the regular way. I wrote the base out however many times, like according to the exponent. So I wrote the base out twice, and then foiled and got that answer. So if I look at the second row of Pascal's triangle, the coefficients given to me are 1, 2, and 1. But if you look at my answer, my coefficients are also 1, 2, and 1. There's technically a 1 here, there's a 2 there, and there's technically a 1 there. So when you do Pascal's triangle, it's giving you the coefficients in the answer, and that's why it's more quick to do it, because then you don't have to do this part.
After you have completed the question, you can check your answer using this final checklist. First, make sure that your x values go down by 1 all the way to 0. After that, you can make sure that your y values go up by 1 and that they stood at 0. And finally, that you've collected like terms. If you have made sure that you've done all this, then you will be on the right track.